Hello my friends, and welcome back to Sky Creative Channel. From the Swiss Alps to the streets of Bangkok, witness the incredible machines and methods that are building the world beneath our feet. Let's get started. And fine. You know, there's something truly remarkable about watching a mountain yield to human ingenuity. Today, we're taking you deep beneath the Swiss countryside to witness one of the most sophisticated tunnel construction projects of recent years. The Eppenberg Tunnel, masterfully executed by the Marti Group, one of Switzerland's most respected construction companies. NTHE Marti Group has been building Switzerland's infrastructure since 1947, and they've become synonymous with precision engineering, which, if you know anything about the Swiss, shouldn't surprise you one bit. This family-owned company has grown from humble beginnings into a powerhouse of construction expertise, specializing in complex underground projects that would make earlier generations of engineers shake their heads in wonder. NTHE Eppenberg Tunnel project represents a critical upgrade to Switzerland's transportation infrastructure, connecting communities through the challenging terrain of the Jura Mountains. This wasn't just about boring through rock. It was about doing so with minimal environmental impact, maximum safety, and the kind of precision that Switzerland has become famous for worldwide. Now, let's talk about how they actually built this engineering marvel. The Eppenberg Tunnel utilized what's called the New Austrian Tunneling Method, or NATM, though it's been so refined and modernized that the new part is almost quaint at this point. This method, developed back in the 1960s, revolutionized tunnel construction by working with the rock's natural strength rather than fighting against it. Think of it like this. Instead of immediately installing a rigid concrete lining, the NATM approach uses the mountain itself as part of the support system. NTHE excavation phase began with something that would look familiar to any miner from a century ago, but with technology that would seem like pure science fiction to them. Marti deployed specialized drilling jumbos. These are massive rigs mounted on heavy-duty vehicles that can position multiple drill arms with computer-controlled precision. Picture a giant mechanical spider, each leg armed with a powerful drill, working in perfect coordination. These jumbos drilled a pattern of holes into the rock face, typically between 30 to 50 holes per round, each one positioned exactly where the engineers calculated it needed to be. Here's where it gets interesting from a historical perspective. Back in the days of building the great alpine tunnels of the 1800s, projects like the Gotthard Tunnel that took nearly a decade to complete, workers drilled by hand with simple steel bits and sledgehammers. A good team might advance 15 feet in a week. Today, with modern drilling jumbos like those Marti used, they can drill a complete round of holes in under 2 hours. The contrast is staggering. Once the drilling pattern was complete, the blast specialist moved in. Now, blasting in tunnel construction is an art form that combines chemistry, physics, and decades of practical experience. The Marti team used precision electronic detonators, a far cry from the simple fuses of yesterday. These modern detonators can be programmed to fire in sequences measured in milliseconds, creating what's called a shaped blast. The idea is to fracture the rock efficiently while minimizing vibration and overbreak. It's controlled chaos, if you will. NTHE explosive charges used were carefully calculated emulsion explosives packed into those precisely drilled holes. When detonated in sequence, the blast would create a cavity that matched the tunnel's planned profile almost exactly. The sequence typically started at the center of the face, creating what's called a cut, and then worked outward in a carefully timed wave. This wasn't the dynamite of old westerns. This was surgical rock removal. And after each blast, and once the dust and fumes cleared through the powerful ventilation systems, the next critical phase began: scaling and support installation. This is where the NATM philosophy really shines. Geologists and engineers would immediately examine the newly exposed rock face, reading it like you might read a book. They're looking for weaknesses, water seepage, changes in rock type, anything that might affect stability. NTHE primary support system installed by Marti consisted of several components working together. First came shotcrete. This is concrete that's literally shot onto the rock surface at high velocity using specialized equipment. The application crew operated robotic shotcrete machines, which could spray a uniform layer of concrete mixed with accelerating agents that allow it to stick and harden almost immediately. This first layer, typically 10 to 15 centimeters thick, acts like a protective skin, preventing the rock from loosening and falling. NBUT shotcrete alone isn't enough for the loads and stresses present deep underground. The team also installed rock bolts, long steel rods that are drilled into the surrounding rock and tensioned or grouted in place. These bolts, often 6 to 8 meters long, act like internal stitches, knitting the rock layers together and preventing separation. Think of them as helping the mountain hold itself up. In sections where the rock quality was particularly challenging, Marti installed steel lattice girders before applying the shotcrete. These prefabricated arch-shaped frames provide immediate structural support and give the shotcrete something to key into, creating a robust composite support system. Watching these massive steel sections being maneuvered into place and connected is like watching a three-dimensional puzzle being solved in real time. The excavation proceeded in what's called a top heading and bench method for much of the tunnel. Essentially, they excavated the upper portion of the tunnel first. The top heading installed its support system and then removed the lower portion of the bench in a subsequent pass. This approach provides better stability and allows for more controlled excavation in challenging ground conditions. It's a technique that's been refined over decades of tunnel construction experience. One of the most impressive pieces of equipment deployed in the Eppenberg project was the tunnel ventilation system. When you're blasting and excavating underground, you're creating enormous amounts of dust, diesel exhaust from equipment, and after each blast, toxic fumes. The ventilation system Marty installed used massive jet fans capable of moving hundreds of thousands of cubic meters of air per hour through temporary ventilation ducts. These ducts, hung from the tunnel crown, ensured that workers always had fresh air and that the tunnel could be re-entered safely after blasting operations. NTHE mucking operation, that's the removal of blasted rock, employed a fleet of specialized tunnel dump trucks and conveyor systems. The efficiency of this operation is critical to maintaining the construction schedule. Marty used 30-ton capacity articulated dump trucks specifically designed for underground work, with low profiles to fit the tunnel section and powerful engines to handle the steep grades often encountered in alpine tunneling. These machines cycled continuously, removing the broken rock and hauling it to the surface where it could be processed and, in many cases, used for other construction purposes or environmental restoration. Water management presents constant challenges in tunnel construction, and the Eppenberg project was no exception. As you excavate through rock, you invariably encounter groundwater. The Marty team installed a comprehensive drainage system consisting of perforated pipes installed behind the shotcrete lining, collecting water and directing it to sumps, where pumps would lift it to the surface. This approach not only keeps the working area dry, but also reduces water pressure on the tunnel lining, which is critical for long-term stability. The more as excavation progressed and the temporary support system proved stable over time, the final tunnel lining was installed. This consisted of reinforced concrete, either cast in place using formwork or, in some sections, using precast concrete segments. The lining serves multiple purposes. It provides the final structural capacity, creates a smooth interior surface for the finished tunnel, and provides waterproofing. Between the rock/shotcrete and the final lining, a waterproofing membrane was installed, typically a thick PVC or similar material that ensures the tunnel interior remains dry even with groundwater present in the surrounding rock. The quality control throughout this entire process was extraordinarily rigorous. Modern surveying equipment, including total stations and laser-based systems, continuously monitored the tunnel's alignment and profile. Any deviation from the planned geometry could be detected immediately and corrected. Similarly, the installed support systems were monitored with sophisticated instrumentation. Extensometers measure rock movement, pressure cells measure loads on the support system, and convergence measurements track any deformation of the tunnel section. This data was analyzed in real time, allowing engineers to verify that everything was performing as calculated or to make adjustments if needed. What really sets modern tunnel construction apart from the heroic projects of a century ago isn't just the equipment, it's the integration of information technology. The Eppenberg project utilized building information modeling, or BIM, throughout its construction. Every aspect of the tunnel, its geology, support systems, installed utilities, and final configuration, existed as a detailed digital model that could be accessed by everyone from the project managers to the equipment operators. This level of coordination was simply impossible in earlier eras. NTHE tunnels' portal structures, the openings at each end, required special attention. These are complex concrete structures that transition from the surface to the underground tunnel, and they must be carefully designed to blend with the landscape while providing structural stability. Marty constructed these using traditional concrete forming techniques, but with architectural details that help them integrate with the Swiss countryside. Environmental considerations included provisions for wildlife crossings and landscaping that would restore the natural appearance of the area once construction was complete. Safety throughout the Eppenberg project was paramount. Modern tunnel construction has come a long way from the dangerous work of earlier eras. The Marty team employed comprehensive safety systems including continuous air quality monitoring, emergency refuge chambers stocked with supplies and breathable air, clear evacuation procedures, and extensive worker training. Hard hats with integrated lights, high-visibility clothing, and steel-toed boots were just the beginning. The safety culture on modern tunnel projects reflects decades of lessons learned, often at tragic cost, about what can go wrong underground and how to prevent it. Looking at projects like the Eppenberg Tunnel, you can't help but appreciate how far we've come. When the first major alpine tunnels were being built in the mid-1800s, they represented the cutting edge of Victorian engineering. Workers labored by candlelight, drilled by hand, and faced dangers we can barely imagine today. The Mont Cenis Tunnel, completed in 1871 after 14 years of work, claimed dozens of lives and stretched the limits of contemporary technology. Today, the Marty Group and companies like them can excavate similar distances in a fraction of the time, with exponentially better safety records, using methods that those Victorian engineers could never have imagined. Yet the fundamental challenge remains the same: convincing solid rock to yield to human purpose, creating passages that will serve communities for generations to come. The Edinburgh Tunnel stands as a testament to both how much has changed and how much remains timeless about this most fundamental of engineering challenges. Now, let's shift our focus from tunnels to another critical piece of underground infrastructure: the installation of overflow spillway gates and overspeed valves. This might not sound as dramatic as boring through a mountain, but stay with me, because the engineering here is absolutely fascinating, and the company behind this work, INAGEN, has developed some truly ingenious solutions to a problem that's been challenging engineers for decades. NNTHE project we're looking at involves installing an overflow spillway gate combined with an overspeed valve in an existing pipeline system. These devices serve crucial safety functions. The overflow spillway gate acts like a pressure relief valve, protecting the pipeline from dangerous pressure surges. The overspeed valve, meanwhile, protects against the opposite problem. If flow accelerates too rapidly, perhaps due to a downstream break, the overspeed valve slams shut to prevent catastrophic damage and water loss. NNTHE installation site is what's called a manhole or access chamber, essentially a vertical shaft that intersects the existing pipeline. This chamber had to be constructed first, and that in itself was an engineering challenge. The INAGEN team excavated a shaft down to the level of the existing pipeline, typically using a combination of excavators for the upper portions, and, as they got deeper, specialized shoring systems to prevent collapse. Once they reached the pipeline depth, the real precision work began. The chamber had to be constructed around the pipeline without damaging it. Remember, this pipeline is still carrying water under pressure. The chamber walls were typically cast-in-place reinforced concrete, formed and poured in sections. Waterproofing was critical. The last thing you want is groundwater infiltrating your access chamber. Modern waterproofing systems use multiple layers of protection. First, a drainage layer against the soil, then a heavy-duty waterproofing membrane, and finally, the structural concrete wall with integral waterproofing admixtures. Here's where it gets really interesting. To install the overflow spillway gate and overspeed valve, INAGEN had to essentially cut into a live, pressurized pipeline. This requires what's called hot tapping technology, a technique that's been refined over decades, but still requires nerves of steel and absolute precision. The hot tap machine is a specialized piece of equipment that gets bolted onto the outside of the existing pipeline after a connection flange has been welded on. This machine contains a cutting tool that can bore through the pipe wall while maintaining a pressure seal. NNTHE cutting operation had to be carefully controlled. The cutting tool, typically a hole saw with carbide teeth, was advanced slowly through the pipe wall. Cooling fluid was circulated to manage the heat generated by cutting. Once the cut was complete, the circular section of pipe wall, the coupon, was extracted back through the hot tap machine, again without losing pressure containment. And then, with the opening created, the installation of the actual valve assembly could proceed. The overflow spillway gate consisted of several key components. First, there was a heavy-duty gate valve mechanism, essentially a sliding steel plate that could be lowered across the pipeline, opening to control flow. This gate was operated by a stem that extended up through the chamber to surface level, where operators could control it either manually or, more commonly in modern installations, through electric or hydraulic actuators. NNTHE overspeed valve component was even more sophisticated. This device had to be able to detect excessive flow velocity and respond automatically. The mechanism typically used a spring-loaded or counterweighted gate that would be held open by the normal flow conditions. But if the flow velocity exceeded safe limits, the increased force on the gate would overcome the restraining mechanism, causing it to slam shut. Installing these components required precise alignment. The valve bodies had to be positioned exactly relative to the existing pipeline, with all connection flanges properly aligned and gapped. Heavy-duty lifting equipment, typically a mobile crane positioned at the surface with the load line running down through the access shaft, was used to lower the valve components into position. NNTHE connection process involved bolting the new valve assembly to the flanges that had been prepared on the existing pipeline. These weren't ordinary bolts. These were high-strength fasteners, often made from specialized steel alloys, torqued to precise specifications using calibrated wrenches. End gaskets between the flanges provided the actual seal. The gaskets used in this type of installation were likely spiral wound metal gaskets or ring-type joint gaskets, both of which are designed for high-pressure applications. Before the system could be considered operational, every component had to be tested under actual operating conditions. The gates were cycled through their full range of motion, multiple times to verify smooth operation. The overspeed valve was tested by carefully creating flow conditions that would trigger it, confirming that it responded correctly. NNTHE's sophistication of this installation reflects more than a century of learning how to manage water infrastructure safely and efficiently. The development of safety devices like overflow spillway gates and overspeed valves came from those hard lessons, each innovation representing someone's realization that there must be a better way. The ability to install such devices in existing infrastructure without major service interruptions is a relatively recent achievement that makes our modern water systems far more resilient than those of previous generations. Let's head to Southeast Asia now, to Bangkok, Thailand, where a completely different approach to tunnel construction is being employed. This is the world of microtunneling, and the company leading this particular charge is Teratech, working on the Green Line cable tunnel project for Bangkok's expanding MRT system. And at the heart of Teratech's operation is the microtunnel boring machine, or MTBM. This is a remarkable piece of equipment, much smaller than the giant tunnel boring machines you might have seen in documentaries about subway construction, but incredibly sophisticated in its own right. The Teratech MTBM for this project was specifically designed for the DN1500 pipe diameter and the soil conditions prevalent in Bangkok. NNTHE MTBM is operated entirely by remote control from a surface control cabin. Operators monitor dozens of parameters in real time, cutting head position, thrust pressure, slurry pressure, advance rate, torque on the cutting head, and the alignment of the machine. Modern microtunnel boring machines use laser guidance systems that keep the machine on course with incredible precision. We're talking about tolerances of just a few millimeters over distances of hundreds of meters. Behind the cutting head, the MTBM has a series of hydraulic jacks that push against the last installed pipe section, providing the force needed to advance the machine. This jacking force can be enormous, hundreds of tons, but it's applied in a controlled, measured way. The machine literally inches forward, cutting and removing soil as it goes. And as the MTBM advances, concrete pipe sections are installed immediately behind it. These aren't ordinary sewer pipes. These are specially manufactured jacking pipes designed to withstand the enormous forces involved in the installation process. Each pipe section, typically about 2.5 meters long, has precision machined ends that fit together perfectly. The joints between pipes are sealed with gaskets to make the tunnel watertight. NTHE pipe installation process is fascinating to watch. At the surface, at what's called the jacking shaft, essentially a deep pit from which the MTBM was launched, a crane lowers each new pipe section into position. Workers guide it into alignment with the last installed pipe, and then the hydraulic jacking system engages, pushing the new section forward and, in the process, advancing the entire string of pipes and the MTBM at the front. It's like a giant mechanical worm, growing longer with each new segment. An NTHE jacking shaft itself is an impressive structure. It had to be excavated to the depth of the tunnel alignment, with carefully engineered walls to prevent collapse. In Bangkok's soft soils, this likely meant using sheet pile walls or diaphragm walls, techniques where reinforced concrete walls are constructed before excavation begins, providing permanent support for the surrounding soil. The shaft also had to accommodate all the support equipment: the jacking frame, the slurry separation plant, the pipe handling crane, and all the pumps and control systems. And at the other end of the tunnel drive is the reception shaft, where the MTBM will eventually break through. This shaft had to be located and constructed with equal precision because the MTBM, traveling perhaps hundreds of meters underground, needs to hit this relatively small target. NTHE slurry separation plant at the surface is a sophisticated facility in its own right. The slurry returning from the tunnel, now mixed with excavated soil, flows into a series of settling tanks and screens. Coarse material is removed first by vibrating screens. Finer particles settle out in tanks, aided by the addition of flocculants, chemicals that cause fine clay particles to clump together so they settle more quickly. The clean slurry then goes to holding tanks, where its properties, density, viscosity, and pH are monitored and adjusted before it's pumped back to the tunnel. NMTHE cables themselves will be pulled through these tunnels after construction is complete. The cable tunnel provides a protected, accessible route for the high-voltage cables that power the MRT trains. What's particularly impressive about TerraTech's operation is the integration of quality control throughout the process. Every meter of tunnel is logged, soil conditions encountered, machine parameters, any anomalies detected. If the MTBM encounters unexpected conditions, such as a buried obstruction or a change in soil type, the operators can adjust machine parameters immediately. Modern MTBMs have enough sensor data that operators can essentially see what the machine is encountering underground. This technology represents a quantum leap from the methods available just a generation ago. The first microtunneling machines appeared in the 1970s in Japan, developed specifically for installing sewers in dense urban areas. The technology has evolved enormously since then, with modern machines like TerraTech's being far more sophisticated, more reliable, and capable of working in a wider range of ground conditions. For a project like Bangkok's MRT expansion, where the city simply cannot afford major surface disruptions, microtunneling isn't just a good option, it's really the only practical option. For our final segment, we're looking at a project that's massive in scale but happens largely out of sight: the installation of the Ugal gas pipeline in Germany, a project where Johann Bunte played a critical role in a major joint venture. This isn't tunnel construction in the traditional sense, but it's underground infrastructure engineering at its most impressive, involving the installation of twin pipelines stretching 60 kilometers, that's about 37 miles, across challenging terrain. NTHE actual pipeline sections arrived at the construction site as individual joints, typically 12-meter-long sections of steel pipe manufactured to exacting specifications. These aren't simple pipes, they're precision-engineered steel tubes with carefully controlled metallurgy, wall thickness, and coating. NTHE construction process began with clearing and grading the right-of-way. Heavy equipment, bulldozers, excavators, and graders created a working corridor typically about 30 meters wide along the entire route. This corridor had to be wide enough to accommodate the trench for the pipes, stockpiles of excavated soil, the pipes themselves as they were being assembled, and all the construction equipment. Trenching for a 60-kilometer pipeline is an enormous earth-moving operation. Johann Bunte deployed fleets of large excavators and trenching machines specifically designed for pipeline work. These machines create trenches with precise depths and widths. Typically, the trench needed to be deep enough to provide adequate cover over the pipes, plus room for the pipes themselves and a bedding layer beneath them. The excavated soil was placed in berms alongside the trench, with strict attention paid to keeping different soil layers separate. Here's where the really impressive technical work began: welding the pipeline sections together. The welding process for large-diameter gas pipelines is a multi-pass operation. First, welders complete what's called a root pass, the initial weld that joins the two pipe ends together. This requires extraordinary skill because the welder is often working in awkward positions and must create a perfect weld with full penetration. And after the root pass, hot pass, and fill passes are completed by welders following in sequence, the weld is inspected using X-ray or ultrasonic testing. And once welded sections have been inspected and approved, they receive their external coating. The factory-applied coating on the pipe joints protects the steel from corrosion, but the welded areas need to be coated in the field. Modern coating systems use multi-layer wraps or shrink sleeves that provide protection equivalent to the factory coating. With sections welded and coated, the next phase was lowering the assembled pipeline into the trench. This required specialized side boom tractors, tracked vehicles with booms extending to the side that can lift and carefully lower the pipeline. Because the pipeline is a continuous welded structure at this point, potentially hundreds of meters long, multiple side booms work in coordination, slowly lifting the pipe and lowering it into the prepared trench. NNFOR, the UGL project, with its double pipeline configuration, this entire process had to be repeated for the parallel line, with careful attention to maintaining proper separation and alignment between the two pipelines. And at river crossings, Johann Bunte likely used horizontal directional drilling, a technique where the pipeline is installed underground by drilling a pilot hole beneath the river, enlarging it, and then pulling the pipeline through. This method avoids disturbing the riverbed and water flow, major advantages from both engineering and environmental perspectives. En-road and railway crossings required similar special techniques. In many cases, the pipeline was installed in protective casings, essentially a larger diameter pipe through which the actual gas pipeline passes, providing mechanical protection and allowing for future maintenance if needed. These crossings had to be coordinated with transportation authorities and often had to be completed during brief windows when traffic or rail service could be interrupted. And once the pipelines were in the trench, backfilling began. This isn't simply a matter of pushing the excavated soil back into the trench. The area immediately around the pipes required carefully selected bedding material, typically sand or fine gravel, that would provide even support and protection from rocks that might damage the coating. This bedding layer was placed carefully, with the trench being backfilled in lifts, layers that were compacted before the next layer was added. This ensures proper long-term support and prevents settlement that might stress the pipeline. Every safety requirement, every inspection protocol, every design standard in modern pipeline construction represents lessons learned. The Johann Bunte team working on UGL stood on the shoulders of generations of pipeline engineers who figured out, often through trial and error, how to safely transport energy across vast distances underground. The result is an infrastructure that's largely invisible, but absolutely critical to modern life, keeping homes heated, industries powered, and economies running, all through pipes buried beneath our feet, installed by projects like this one that combine massive scale with meticulous attention to detail.